Hello everyone. In this video, I'm going to present electrostatics, and more exactly, this presentation consists of these topics, focus on these topics, which are Coulomb's law of electrostatics, and a relation between electric field intensity and electric potential, and the concept of electric flux, then Gauss law of electrostatics, and in what way this Gauss law can be applied. I mean, to find the electric field intensity, due to these charge distributions. This charge distribution includes zero dimension, I mean point charge, and one dimension, infinite line of charge. I mean, the charge is distributed along the line, and a two-dimensional charge distribution, which is infinite sheet of charge. But in order to proceed this, first we'll try to understand the basic entity of this electrostatics, which is electric charge. So generally, electric charge is an elementary entity, and this electric charge is carried by either excessive of electron, and generally we will say negatively charged particle, or even it is possible if there is any deficiency of electron. So if there is any deficiency of electron, we will say positively charged, and we will measure that the reference to measure the electric charge is electron. So that excessive of electrons or deficiency of electron may be more than one also. So that's why in general we will write n times to the electron. And then the elementary entity charge of the electron is 1.602 into 10 to the power of minus 19 Coulomb. Now even we can calculate the amount of, I mean number of charges. If I say the current is 1 ampere, and if you see the basic definition of current, electric current, I is charge flow per unit time. Charge flow per unit time. Whether it may be positive charge or negative charge. So it will be N E by T. And we will measure that as per the definition, it is per unit time. So we will take this unit time as 1 second. This is equal to what? 1 ampere, right? So now we can write the equation like number of electrons is equal to 1 ampere. So now we'll calculate the N number, which is 1 by E ampere, 1 by E. So this N is 1.6 into 10 to the power of minus 19. And if you calculate this, around 0.6 into 10 to the power of 19. I mean 6 into 10 to the power of 18. So this much number of electrons, this much, I mean 6, approximately 6 into 10 to the power of 18 number of electrons should flow in 1 second, then that number will consider as 1 ampere. Then now we'll take two such charges. Either it may be both are positive charges, or it may be both negative charges, or one may be positive, one may be negative, in any combination. Out of that four, you can choose any combination. And this Coulomb's is given some conclusions, the interaction, force of interaction between two charges. And his conclusions was the electrostatic interaction between the two charges is proportional to the magnitude of the two charges we considered. And another conclusion is inversely proportional to the square of the distance between them. I mean, in the sense, if you show that in diagrammatically, let be this is charge Q1, and let be this is charge Q2. I mean magnitude of both the charges are Q1 and Q2, and both the charges are separated by distance r, and of course we are taking the shortest distance is r, and as per his conclusions, the force of interaction between these two charges will be proportional to magnitude of the two charges and inversely proportional to square of the distance between them. And this force is a vector. So even we can the force is a vector. Even we can define its direction also. So its direction will be along the line joining of them. I mean, this is the line joining between the two charges. So along the line joining between them will be the direction. I mean, either it may be Q1 to Q2 or Q2 to Q1. That depends on for which charge we are calculating that force, and we'll represent that mathematically. I mean, like this. F is capital Q and small q, and these are the both charges, and the distance between the two charges is r, so 1 by r square. I mean, if you consolidate them, so F is proportional to capital Q small q by r square. And if you remove the proportionality, and we can replace that with some constant k, and more exactly, the constant is 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught small capital Q small q by r square. I mean, product of the two charges by distance between them. And where this epsilon naught is a constant, and if it is epsilon naught, this is defined for free space. And depending on the medium in which these two charges are placed, accordingly, we need to choose this constant. Right now, we'll consider that two charges are in free space. So here that epsilon naught will be permittivity of free space. And in free space, generally the value of the permittivity will be order of 8.85 into 10 to the power of minus 12 Coulomb square per Newton meter square. So that the constant k will be, I mean, this constant k, which is equal to 1 by 4 pi epsilon naught, is 9 into 10 to the power of 9. I mean, here this k is 1 by 4 pi epsilon naught. I mean, if you substitute that like 1 by 4 into 3.14 into 8.85 into 10 to the power of minus 12 with units. So this value is 9 into 10 to the power of 9 Newton meter square per Coulomb square. And this equation, we already said, this is in free space. I mean, what does it mean? The two charges are placed in free space. If that both is same charges are placed in a medium, then that equation will turns to, I mean, instead of epsilon naught, we'll write this as epsilon, right? And here that epsilon is, this is also permittivity, but this is permittivity of free space. And if you are interested to write this equation in terms of free space, I mean, even though these two charges are placed in a medium, but still, if you are interested in terms of free space, now this epsilon is replaced with what? Epsilon r and epsilon naught. I mean, this relation is came from this definition. Epsilon r is relative permittivity. I mean, relative in the sense, generally we will give the value of permittivity value relative to the free space. I mean, that's why it is denominator. I mean, in the sense, let be epsilon r value is 4. 4 for any medium, randomly some medium, epsilon r is 4. What does it mean? The permittivity of E is 4 times to the permittivity in free space. I mean 4 into 8.85 into 10 to the power of minus 12. That is mean by epsilon r. So till now, this equation shows only the magnitude. But even we can write that in vector also, because this Coulomb's law is explaining about force of interaction. So if force is vector, we can represent that in vector form also. And if you write that in vector form, as we said in conclusions, the direction of force will be along the line joining of the two charges. I mean, r cap. R cap is unit vector of that distance. And this is in terms of unit vector. And you can write that in actual vector also. And what does it mean? Let me, this is capital Q. And this is small q, second charge. Both are separated by a distance r. Now you are saying this is vector. Now let be this line, I mean this r is made by a small segment, and we'll say the small segment is r cap. Now if you translate this small r into some number of times, if you translate that small r into some number of times, you'll get the actual vector r cap. So now you can write like this. This r cap is made by unit vector r cap by translating how many times? As per our example, 5 times. So 5 is the magnitude, right? I mean this vector r is magnitude of r into r cap. Now you can write this r cap as what? Actual vector r by its magnitude. Now you can see there. So in magnitude, that power is increased to 3, right? And instead of r cap, it will be actual vector r. This equation is in free space. Similarly, if you write that in medium, so instead of epsilon naught, we'll write that as epsilon. So if it is r cap, it should be r square. So now this is Coulomb's law. Coulomb's law both in scalar form as well as a vector form in free space as well as in any medium. But now the question is, and if you see the two charges, plus Q and capital Q, there is no direct contact between these two charges. But still, there is no direct contact between these two charges, but still some amount of force is existed. But how this is possible, even though there is no direct contact between them? Sorry. And not only, I mean, this concept is not only for two charges. The same behavior we can also observe in case of magnetism also. So where the two poles M1 and M2, even though there is no direct contact between these two magnets, still there is a force of interaction. And not only for magnets, gravitational force also. I mean, if you just release the any object, it will attracts to the ground. There is no direct contact between the earth and that object, but still forces existed. So all these type of forces are generally called as non-contact forces. And in order to understand, I mean, even though there is no direct contact, how that force is possible, in order to understand, we'll generally define a quantity which is electric field intensity. And we'll see that in next slide, of course. Now the question is it possible? Is it possible to apply this Coulomb's law more than two charges? I mean, let me, we will take for three charges, Q1, Q2, Q3. Is it possible? Yeah, definitely possible. But for that, we need to apply some number of times. I mean, if three charges you are considering, then we need to apply Coulomb's law 2 times. And the principle of superposition says that if uh, if that number of point charges R is greater than 2, then the total force on a particular charge will be equal to vector sum of forces. See, here we are not saying a general sum, we are saying the vector sum. What does it mean? We need to consider not only the magnitude, but also the direction of force also. So that is the vector sum of the forces due to other two charges, right? I mean, or you can say other all charges. This is a principle of superposition. What does it mean? We will try to explain with some mathematical equations. So let be we will consider three charges. Three charges. Let be this is Q1 and let be this is Q2 and this is Q3. Now Q1 and Q3 are separated by R13 and Q2 and Q3 is separated by R23. Now we are calculating the force. Force on which charge? Q3. So now that force on Q3 will be due to both charge Q1 as well as charge Q2. So now write the equations individually and then we'll do the vector sum. Now see here. This is force due to Q1 on Q3. Both are separated by R13. And this is force due to Q2 on Q3. Right? And both are separated by R23. So first we'll write that individually and then we'll sum up, vector sum up. But if the number of charges are 100 in number, so that equation will be very lengthy. In order to write that in simple way, we will use that mathematical tool, which is sigma, sum. And that equation will be 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, Qij by Rij square. So where this J, we are calculating the force on jth charge. Let be nth charge. Then this I will starts from 1 and 1 to n minus 1, right? And if I, as per our example, J is 3. And we are applying that equation in how many times? N minus 1 times. This I is equal to, we'll apply that up to n minus 1 times. So you can apply that Coulomb's law even though the charges are more than 2 also. But of course, we need to apply that for n minus 1 times. Now, as per our discussion, so how to explain these non-contact forces? And for that, generally we will define a quantity of the concept of electric field intensity. So here the field. So here the field is the field of what? This electric charges. Right? As per our regular discussion, even though there is no contact, there is a force of interaction is there because every charge is having some region. Every charge is having some region, whether it is positive charge or negative charge. If it is positive charge, every charge is having some region. So if any other charge is within this region, then definitely there will be force of interaction. If it is away from this region, there will be no interaction. So now, as per our diagram, this is the vicinity of this charge, where the other charge can experience that force. And this region where the other charge can experience that force is called field, electric field. Now the question, is that intensity, is that force of attraction or force of repulsion will be same at all the points? So definitely not. We will try to explain that. Let we are taking a positive charge Q. And now this positive charge is having some region, and in that region, if you place other charge, definitely it will feel some force of experience. Now we'll try to visualize. We'll try to draw the diagram for that. Now you can see this is the entire region, this outer circle, and this diagram I'm trying to explaining that. If any other charge is placed up to this region, see the thickness of line is more. What does it mean? It will attract more or repel more. As you are moving away from that plus Q, I just shown that with a little bit thinner. That force of attraction or force of repulsion will be little bit less. So as you are moving away from the charge, the effect of that plus Q will be also decreases. So here that intensity of attraction or intensity of repulsion will not be same at any point. That will be different at a different point. So that's why generally the electric field intensity is calculated at a given point, at a given point, because at different points that intensity will be different. So due to that, randomly now we'll taking this particular point Q, this particular point, and the charge is placed, and we will say this is test charge, right? Now that force of course, now this charge test charge is within the region of this plus Q. So effect definitely will be there. So that effect will definitely depends on what is the magnitude of this Q, whether you are placing that plus Q as 1 Coulomb or 2 Coulomb or 3 Coulomb and so on. If more the charge of this test charge, the more will be the interaction, right? What does it mean? You can simply say that the force produced by this plus Q on this test charge will be depends on the magnitude of the test charge, how much charge you are placing. So this force by plus Q is proportional to the test charge, magnitude of test charge. Now we'll remove this proportionality and we'll define the concept of electric field, right? And now we'll give the definition for this. This E is equal to what? F by Q. So intensity of electric field at this given point will be equal to how much force, how much force experienced by the test charge. And I already said the test charge may be that your choice, maybe 1 Coulomb or 2 Coulomb or 3 Coulomb. If you place the if you place the large amount of test charge, then the electric field intensity will also be high. So that's why the better way to measure is always measure per unit charge. I mean, if you place 1 Coulomb and you are placing 2 Coulomb, definitely this electric field intensity will be more for 2 Coulomb, and electric field intensity will be more for 3 Coulomb. Then which one will be right? So that will be give the contradiction. So that's why it is better way to measure what you can place any amount of charge, but it is better to measure per unit charge. I mean, that is standard way to measure the electric field intensity. So the conclusion is you can keep any amount of charge, but the standard way of measuring is measure that always per unit charge is electric field intensity. And of course, that will be different at different point. And another way to understand the non-contact forces is electric potential, capital V. And we'll try to explain the concept of electric potential. So for that, first we'll consider a uniform electric field. Uniform in the sense, at any point, the electric field intensity, magnitude of electric field intensity will be same, and they will be in same direction. All these lines will be in same direction. Now, this uniform electric field, randomly you are selecting a particular point A, and where the charge Q is placed, right? I mean, what does it mean? A charge Q is placed at point A in uniform electric field. Now, our interest is to move the charge, to move the charge plus Q from point A to point B. So in order to move this charge from point A to point B, definitely we need to apply some external force. So by itself it cannot move. Definitely we need to apply some external force by some means. So if it is displaced, because it is changing its position from point A to point B, is nothing but it is definitely displacing. So if that force is causing displacement, definitely some work is done, right? Some amount of work is done in order to move the charge from point A to point B. And of course, the force you are applying is against to the electric field. Against in the sense, electric field is let be in positive x direction, but the displacement is in negative x direction. I mean, you are doing that work against to the electric field. But how much that force will be equal to that, as per our previous slide, that F is equal to how much force that we need to apply, external force QE. I mean, that depends on electric field intensity at this given point. And if you calculate the work done, external work done, as per this F dot X, dot product of force and displacement, Fx cos theta. And here, that external force is in negative direction because you are moving that from A to B, and the displacement is also in negative direction. So here the theta is 0 degree. So cos 0 is 1. So that F external into X. And this amount of external force that we need to apply is QE. So that external work done is QEX. Right? But why we need to apply external force on this charge? Because against to that electric field is there. What does it mean? We are applying this force against to electric field. Is nothing but that electric field is also doing applying some amount of work. I mean, what does it mean? We need to apply that external force in order to move the charge from point A to B, because that electric field is doing also some work. I mean, against to that we need to move. That's why external force is required. I mean, if you do the same calculation in terms of electric field, I mean, work done by electric field is same equation F dot X, but here that force is force due to electric field. So FEX cos 180 degree. So here that 180 degree, because see there, electric field in positive x direction, but the displacement is electric field is in positive x direction, but the displacement is in negative x direction. So now both are separated by 180 degree. So cos 180 is minus 1. So that minus 1 F external x minus QEX. So the magnitude is same. The only difference is whether you are calculating that work done is due to external force or is due to electric field, right? And this work done is stored as potential, potential energy. So this delta U change in potential is UB minus UA, which is minus QEX. If this UB is at infinite, if this UB is at infinite, the delta U will be minus QEX. I mean, we'll try to understand this particular statement a little bit clear. So let be this is electric field. Let be this is constant electric uniform electric field. So here the point A. Now let be initially the charge is at infinite distance. Here infinite in the sense out of the region, out of the electric field region, anywhere. So let we are considering that all that region which is electric field region, let be infinite, and somewhere here I'll choose somewhere here. Initially charge q is here. Now you are bringing this charge from outside the electric field to point A. So definitely we need to do some work against to the electric field. So that is UA, potential at this point. I mean, we need to overcome some electric field energy. Similarly, the same charge is moving from infinite to somewhere B. So here also we need to do some work against to electric field, that is UB. So potential at B is UB, potential at A is UA. Now in our case, now you are moving the charge from A to B. So that will be the UB minus UA, final minus initial, UB minus UA, that is potential difference. So here we said if UB is at infinite, what does it mean? That point B is out of the electric field region. So out of the electric field region, there is no potential, no need to do the work. And if you are interested to move this charge from somewhere else to this B, I mean, let be that point B is here, somewhere else to here. So now this region is not in electric field region. So there is no need to do the work. Of course, we need to do the work, but no need to do the work against to the electric field because this effect is not there in this region. So here that potential is zero. I mean, of course, we need to do the work, but that work is not against to the electric field. So that's why potential is zero. Right? This is the concept of electric field, electric potential. Now we'll try to give the relation between both these electric field as well as electric potential. We'll try to give the relation between these two physical quantities. We'll give the relation both in integral form as well as differential form also. So now let be these are 2 points, point 1 and point 2. I mean, like previously we considered point A, point B. I mean, now these 2 points are in electric field. I'm just not drawing in uniform electric field. Now our wish is to move the charges from point 1 to point 2. So for that, what we'll do? First we'll take a small segment dx. When this total length is x, but we'll take a small segment dx. So if charge is displaced from point 1 to 2, the work done should be W. If the displacement is a small segment dx, then the work done will be dW. Right? So what does it mean by that? The work done to bring the charge, to displace the charge, an amount of dx is minus f dx. Here, the minus is indicating that that work done must be against to the electric field, against to the electric field. So this force is equal to QE dx. So dW is minus QE dx. So this work done, I mean, point 122. I mean, now if you calculate the total work done, just we need to integrate this E dx from point 1 to point 2. So Q is of course constant, so that's why you can write out of the integral. So 1 to 2 E dx. This is total work done, and this work done is stored as potential energy. So that electric potential is V2 minus V1. Final minus initial will be minus 1 to 2 E dx. So now this is relation. This is relation between electric potential and electric field intensity. Now, in some cases, generally, if we let be, if initial point, I mean, this initial point is at infinite in the sense out of the electric field region. What does it mean? Its potential is zero. I mean, no work is required against to the electric field. So potential is zero. So that V2 will be V. So this is electric potential, electric potential in terms of electric field in integral form. Now we'll write the same equation. I mean, relation between electric potential and electric field intensity. Electric field intensity. Now we'll write the relation between electric field intensity and electric potential in differential form. Now, from the definition of potential, this equation came from potential is work done to bring unit charge within the electric field. So V is W by Q. If that work is small, if the displacement is small segment, we say that is dW by Q, which will be equal to what? Which will be equal to dV. So the dWb equal to what? Q into dV. So small amount of work done, right? To displace small amount. dW is equal to QD. But from previous equations, just previous slide, dW is equal to what? Minus F dx. That is the definition of work done. Force dot displacement. So minus QE dx because that force is QE. So if it is dot product Q as it is. Now here the dot product is in between E and dx. So minus Q E cos theta dx. I mean you are giving the equation for work done in two ways. Right now compare both the equations because both are for work done. Both equations are for work done. So if you compare or equate both equations, so see here Q dV is equal to minus Q e cos theta dx. On both sides, Q will be cancelled, right? So that e cos theta is equal to what? E cos theta is equal to dV by dx, dou v by dou x with minus. I mean, if the displacement is along the only x direction, that's why we took partial differentiation minus dou v by dou x. So the displacement may be in y direction also. So in that case, the format is same, but we need to just change the coordinate minus dou v by dou y. And if the displacement along the z direction, minus dou v by dou z. If you are interested to say that in three dimension at a time, so this electric field E will be minus dou v by dou x dx. Again minus dou v by, now here it is y coordinate dy minus dou v by dou z dz. And if it is only along the y direction, then we will take the partial differentiation minus dou v by dou x. Now see there, this is differential form. I mean relation between electric field intensity and electric potential in differential form. Now we'll come to the concept of flux. So this is common word for any non-contact force related fields. Flux in the sense number of field lines. Number of field lines. This is general definition. Whether it is electric field lines or magnetic field lines, the format is same. Number of field lines. But the number of field lines should penetrate through the surface. Of course, number, but the number must be how many field lines that are passing through the surface. So number of field lines passing through the surface is flux. I mean, see here. Let be this is the surface, and these are all electric field lines. So as per this diagram, the flux will be equal to how many number? One, six. This is six. But mathematically, as per the definition, the equation will be electric field intensity into A. This is the product of E into A. But this is not the standard way to define the flux. Standard way to define the flux. Then what will be the standard way? I mean, here something is missing. I mean, in the sense, if you apply this equation theoretically, the result which we obtain is not exactly matching with the practical result. I mean, if we measure the flux with any device, I mean, practically, so that result and this equation result are not matching. So something is missing. I mean, if you measure this in this way, something is missing. Then later on, it is standardized. The standard way to measure the flux is, of course, we need to measure the number of field lines. And of course, they should be passed through some area, but it should pass through that area perpendicularly. I mean, we need to consider the electric field lines which are passing through that area only perpendicularly. In the sense, let me, this is a small segment dA, a small area dA. Now we'll take one particular field line. Now see here. Now this is exactly perpendicular to the surface. Right? This electric field line This electric field line is exactly perpendicular to the surface, right? But if you choose now we'll choose another electric field lines randomly. Now this is not perfectly perpendicular. This electric field is not perfectly perpendicular. I mean, if we go through the previous definition, the flux should be 2, right? The flux should be 2. But if you measure that 2 units, if we measure that practically, that result is not coming to be 2. The result is coming to be randomly less than 2, let be some 1.5. So here we will count this as 1 perfectly, but we should not count this as perfectly 1, it is less than 1 because it is not perfectly perpendicular. So what we'll do, we'll do one thing. We'll resolve that vector into two components. We'll resolve that vector into two components, right? This is component 1 and this is component 2. And their components are, if this is theta, then the components will be e cos theta and e sin theta. Now see here, the contribution of this electric field which is passing through the surface is not entire E, but a part of E, e cos theta, right? E sin theta is not passing through the surface perpendicular, only E cos theta is passing through that. So what should be the flux? The first E, I mean total magnitude of that first line, but not the total magnitude, only E cos theta of second line. So that's why it is the standard way to measure is only perpendicularly. And if you show that in equation format, I mean pi is equal to E cos theta dA. What, because this is E dot dA. We need to consider the direction of E also. So as per the dot product, E dot dA is E cos theta dA. Then E dot dA. If you are calculating for entire surface, I mean the total surface, I mean, let be the slide is made by these small segments dA. Then of course we'll integrate that E dot dA. And overall in this slide, we need to notice two things. Here in integral, we are showing some a symbol like enclosed. I mean, this integral is enclosed by such some circle. This is closed integral, or more strictly, you can say that surface should be closed surface. And number two, you can define this definition in two ways. The one way, I mean, seems to be little bit confusion, but if it is clear, it will be very easy. The one way of define is perpendicular to surface, perpendicular to surface, as here it is mentioned. Another way, parallel to, of course, surface, but it should be parallel to direction of surface, direction of surface. So what is the difference between these two? I mean, all this explanation is through this first point, the direction of surface in the sense. If this is the surface, not only the surface, the direction of any surface is just draw the perpendicular to that surface. That will be the direction. I mean, this is dA. Direction of this surface is dA vector, which is perpendicular drawn to the surface. Now, see here, that's why the cos theta component is, which is the direction of surface. I mean, this you are taking as a reference. This is we are taking as a reference. That's why the theta is here, not here. Because we can keep that theta anywhere, here also, and I mean you can keep the theta here or even here. We place it the theta here because this line is the reference, which is the direction of surface, right? Now see here. Now we'll explain that in two ways. Now this E cos theta is perpendicular to the surface in another way. This E cos theta is parallel to direction of surface. So that's why the theta is taken here. And this the first point we choose. What is this mean by the closed surface? We'll see that in next slide. So for that, we'll go with that Gauss law of electrostatics. There you can now in this Gauss law of electrostatics, we'll try to explain what does it mean by that closed surface also. First, we'll see this significance. I mean, what information generally we obtain with this Gauss law of electrostatics? The significance of this law is it will correlate the flux, electric flux phi through here, through any closed surface, through any closed surface to the net amount of charge within the surface, right? I mean, if you write that statement, I mean, what is that relation? What is that exact relation between that flux and charge? That statement is the total flux through a closed surface enclosing, this closed surface is enclosing a charge. The flux due to this enclosed charge is equal to 1 by epsilon times to the magnitude of the charge enclosed. I mean, if you write that in mathematical form, see here, the total flux through a surface, let be this is surface. The total flux through this charge will be equal to what? The charge enclosed. The charge enclosed by that surface. This is must be enclosed charge. I mean, it may be some little bit like abstract. We'll try to fulfill this. For that, I will take some number of diagrams. Now, this is open line because initial and final point is not met again. Now, this is closed line. This is closed line, right? This is closed line, or you can say open surface. Open surface because this surface is not enclosing any volume. Now, see the sequence. This is open line because this line is not enclosing any surface. Now this is open surface because this surface is not enclosing any volume. Now then what does it mean by closed surface? Just here, closed surface. Now randomly I will take this as a surface. Now this is open surface. Now if that surface is enclosing any volume, now this is volume, right? Now this surface is closed surface. Like like if you take a bottle cap, if you take a bottle cap, now this bottle cap is open surface. Here we are not taking the bottle, we are considering only the cap. Now this is open surface. Now if you close this cap to the bottle, if you close this cap to the bottle, now this surface, I mean this cap is closed surface because this is enclosing some volume. This is enclosing some volume, right? So closed surface in the sense this surface is enclosing some volume. Here open surface in the sense now the surface is not enclosing any volume. Now if you take some charge q in this volume, now this is enclosed charge because this charge is enclosed by this surface, right? So as per the definition of this, as per the definition of this Gauss law, now you may understand very clearly the total flux through the closed surface. I mean, let be this is closed surface because the surface is enclosing some volume. So the flux, I mean, number of field lines passing through this closed surface is equal to 1 by epsilon naught times enclosed charge. So this flux is equal to 1 by epsilon naught times Q. So from overall this discussion, one thing that we should notice is that Gauss law of electrostatics is strictly for closed surfaces. Gauss law of electrostatics is strictly applicable for closed surfaces only. I mean, it is not applicable for open surfaces. It is applicable for only closed surfaces only. And we'll try to prove this equation mathematically. We'll try to prove this. So in order to prove that, just here, let me this is surface. And as per our the previous statement, it is a closed surface. What does it mean? This surface will encloses some volume, and in that surface, let we will consider a point charge. I mean, this surface is enclosing some charge Q. See, this is two-dimensional view. I just previously drawn the three-dimensional view, but however, I will still draw it. Now this surface, yes, is enclosing some charge Q. What does it mean? This is Q enclosed, enclosed by the surface. Now in that surface, we will select a small segment, a small area of ds, a small element of ds. Now let we'll consider point P. In that point, in that small element ds, we'll consider point P, and through that point P, that one of the electric field line is passing through that unit surface. What does it mean? This plus Q will produce electric field in all possible direction. But out of all that electric field lines, now you are considering an electric field line which is passing through this ds. I mean, this is passing through the ds. Now, this is the direction of surface, ds, the second line. I mean, normal drawn to the surface is the direction of surface. You can write like n cap or ds cap. ds cap is the direction of surface. I mean, the direction is just draw the normal to that. Now, see, both are separated by theta. What does it mean? This electric field line is not exactly perpendicular to the surface. It is making an angle of theta. Now, for this, I mean, for this, I mean this ds elemental surface ds is making some solid angle with the q, solid angle with the enclosed charge q, right? I mean, we will try to draw this a little, I mean, in three dimensions. It's better to try. We'll try to draw that in three dimension. Let be this is ds. Let be this is ds. I mean, of course, closed surface. What does it mean? The surface is enclosing some volume. Enclosing some volume. I mean, the surface is enclosing some amount of charge also. Now, this charge is producing electric field in all possible direction. But now you are selecting a differential surface ds, a small surface ds. I mean, this is electric field line passing through that. One of the electric field line passing through this surface ds. But if you draw the direction of the ds, I mean normal to the ds, this is direction of ds, normal. This is theta. Now this charge q is making a solid angle d omega. D omega, solid angle d omega, solid angle d omega here. Right, this is three-dimensional view of this diagram. So now we'll calculate the electric, first we'll calculate the electric flux. I mean the number of field lines which are perpendicular to that surface is ds, only through ds. So as per the definition of flux, d pi, I mean flux through that small element ds will be E dot ds. So dot product of E and ds will be E cos theta ds. And from the definition of electric field, from the definition or equation of electric field, this electric field intensity due to this charge will be 1 by 4 pi epsilon naught q by r square. Just you are substituting the equation of this electric field. So 1 by 4 pi epsilon naught q by r square, and remaining as it is cos theta into ds. And where this r is the distance of the surface element to charge q. I mean this is r. This distance is r. But however, this ds cos theta by r square, ds cos theta by r square will be the solid angle. I'm not going in detail proof of this mathematical version. The ds cos theta by r square is equal to a solid angle d omega subtended at charge q. I mean, instead of that, you can replace that as d omega. But I can give some comparison for a little bit simple logic. If you take plane angle like circle, then this is plane angle theta. This is arc length S and this is radius R. So this theta is equal to arc length is S and radius R. See here, arc length. I mean, this is length. Radius is also length, right? So for two-dimensional angle, I mean plane angle, it is the ratio of length by length. But here solid angle, I mean three-dimensional angle. Accordingly, there is area by area. ds is the area, r into r is area. Just a little bit comparison, not comparison, like similarity. For two-dimensional angle, it is the ratio of length by length. For three-dimensional angle, it is the ratio of area by area. Right? Now we'll replace this. We'll replace this equation. I mean, we'll write this ds cos theta by r square as d omega in this equation. So if you write that, the d pi will be 1 by 4 pi epsilon naught into q as it is, into q as it is. Let me this capital Q as it is, and remaining term will be d omega. But this is flux through only this small element. But we need to measure that flux through this total surface. So for that, just we need to integrate this. Right? Total flux through the entire surface will be just integrate that. Pi will be equal to what? Integrate the d pi and integral eds. So here we mentioned that. See there, this surface is a closed surface. And we already written this d pi. So 1 by 4 pi epsilon naught q. All these are constants. So you can write that out of the integral d omega. And that solid angle will be 4 pi. This d omega. I mean, if you integrate that, the solid angle will be d pi. What does it mean? This entire surface is making an angle of 4 pi. And if you simplify that, this pi is equal to integral eds. This 4 pi and 4 pi will be cancelled, and remaining will be 1 by epsilon naught times q enclosed. So this is the proof of Gauss law. So in what way it is advantage? What way it is advantage? So with this Gauss law, here we need to mention we need to mention it. See here, integral E dot ds. Integral E dot ds is equal to what? 1 by epsilon naught times q enclosed, which is equal to pi. The advantage of Gauss law is you can calculate the electric field intensity a little bit easier. Of course, if the charge distribution is continuous, integral is generally used for continuous functions. If the charge distribution is continuous, then we can apply this Gauss law so that the calculation of electric field intensity will be a little bit easy. In what way? We'll see that applications. If we go through that application, then we can understand what is the advantage of this Gauss law, right? But before that, we'll write this Gauss law. We'll write this Gauss law both in integral form as well as in differential form. So first we'll go with this integral form in of Gauss law. If you see the previous equation, we already given this equation in previous slide. The total flux through the closed surface, closed surface is equal to what? 1 by epsilon times to the enclosed charge. And we'll write this epsilon naught because it is constant, right, left side. So that the equation will be as it is. Integral, closed surface integral, closed surface integral of epsilon naught E ds is Q. And here we will define one more quantity, which is displacement vector D. What does it mean? Just we replace the epsilon naught E as D. And we will try to give the analogy for this D in magnetostatics also. I mean, you can write that Gauss law both in terms of electric field intensity or displacement vector D. Right? D is also electric field quantity, but a little difference will be there. We'll see that later on. We'll say the displacement vector. Basically, this is also electric field intensity. You'll see that later on difference. But however, the conclusion is you can write the Gauss law both in terms of electric field intensity, in terms of displacement vector. So both are related with what? That capital D is equal to epsilon naught E. And if you see this equation, the left side is okay. The left side is in integral form, but the right side is not in integral form. So we need to change this. In order to write the total in integral form, we need to change this Q and we should write this in integral form. It is better to write this in integral form. So for that, what we need to do? Just see here. We already said flux through that surface. That particular surface is enclosing a volume. I already said this particular surface is enclosing some volume. This is surface enclosing the volume. Then the charge. We are saying that that amount of charge is Q. You can represent the charge or even you can represent that as a charge density. Charge density is charge per unit volume. So what does it mean? You can write this Q as was rho into V, right? Rho into V. Now if you see this, if you understand this, just see the modification. So now you can write this Q as, if you can write this Q as integral V rho V dV. What does it mean? This is dq and this small amount of charge if that volume is dV. I mean, you are selecting a small segment of volume in this. In this small segment of volume, the amount of charge is dq. So total charge will be equal to what? Integral dq. Now, I mean, you are changing the charge in integral form. Now see the previous equation. This is where we closed. Integral closed surface integral E dot ds is equal to q. But now that q can be written as this integral v rho v epsilon naught dv, rho v epsilon naught dv, right? Or you can write that equation in terms of displacement vector also. You can write this epsilon naught product of, I mean coefficient of this e. Now see that both sides of the equation is in integral form. So in terms integral form in terms of electric field intensity or in terms of displacement vector. And We'll write the same equation, Gauss law of electrostatics, but in differential form, right? For that, first we'll take the integral form of that equation. As per our previous slide equation, integral closed surface integral E dot ds is equal to volume charge density by epsilon naught into dv, right? And for that, we'll apply the Gauss divergence theorem. Uh, Here, the purpose of applying the Gauss divergence theorem is because of course, this equation is integral form, but if you see, there is not uniform. The left side is a surface integral. What does it mean? A double integral. And the right side is triple integral, volume integral. Triple integral will be there. Of course, in integral form, but not uniform. So we'll try to make this integral form equation uniform. Either both sides should be surface integral or both sides should be volume integral. So in order to convert that surface integral to volume integral or volume integral to surface integral, generally Gauss divergence theorem is used. So the significance of Gauss divergence theorem is you can convert surface to volume integral or volume to surface integral. And as per Gauss divergence theorem, you can write this surface integral in volume integral. This closed surface integral E dot ds is equal to del dot E dv. Here, the del dot E is divergence of electric field. Divergence of electric field. What does it mean by that? We'll try to give the physical interpretation for this. So let me will start with beginning. Let be this is closed surface. Yes. What does it mean? This surface is enclosing some volume. Enclosing some volume. And this surface is enclosed some charge Q. Now this charge is producing the electric field in all possible directions. So out of that, the perpendicular contribution of electric field is the flux. Perpendicular, the number of field lines which are passing perpendicularly only is the flux. So the flux is coming out from the surface also in all possible direction. See that here all the electric field lines are starting from one point, but they are spreading. They are spreading in all possible directions through that surface. So mathematically, generally, the nature of this spreading is explained mathematically with divergence, del dot that vector. Here that vector is electric field. So what does it mean by that? Del dot E in the sense that electric field is spreading, coming out from the volume, right? So the surface integral, closed surface integral, E dot ds is equal to del volume integral del dot E dv. Now you can exchange surface to volume or volume to surface. But which is better? Generally, volume integral is easy compared to surface integral. So that's why just here. So these are the two equations. This is actual equation and this is from Gauss law. If you compare both are at E dot ds. What does it mean? You are changing the surface integral to volume integral because volume integral is easy compared to surface. So del dot E dv is equal to rho v by epsilon naught dv. See, both sides are volume integral and both are for same volume. Both sides volume integral and both are for same volume. So that you can cancel out, see the remaining. The remaining will be what? Del dot E is equal to rho v by epsilon naught. This is in terms of electric field. And you can write that in terms of displacement vector also, just by bringing this epsilon naught to the coefficient of electric field. So that del dot D is rho v. Now here, see here, this is differential form. I mean, you may ask, where is the differential form? Generally, del is a uh, vector operator, which is equal to I dou by dou x plus j dou by dou y and k dou by dou z. If it is with dot product, then I dou d by dou x, dou d by dou y, dou d by dou z. So here the differential form. So we given the Gauss law of electrostatics both in integral form as well as the differential form. Now we'll see the applications. We'll see the applications. I mean, I already told you the calculation of electric field intensity will be a little bit easier if you apply the Gauss law of electrostatics. In what way? First, we'll go to the one zero dimensional point. I mean, point charges. So for that, let let be this is charge q, and around that we'll consider a surface ds. I mean, this charge is enclosed by this. I mean, previously it was we took a randomly some random surface ds, but now we are taking the Gaussian surfaces. I mean, which are symmetrical. Gaussian surfaces are generally symmetrical in nature. Now that closed surface is in which shape? I mean, spherical shape, right? I mean, this surface is enclosed in the sphere, right? So now in this Gaussian surface, the plus q is it exactly in middle. And out of that entire surface, now just imagine like a point charge q is placed in a rubber ball. I mean, inside the rubber ball, there is, I mean, no material will be there. It will be only air. Right? Just imagine like a charge q is placed in rubber ball. Now this is the surface element. I mean, on the total surface, first we are selecting only a small segment, ds. A small segment. This is ds. And what is the direction of this ds? Just draw the normal. Direction of ds is just draw the normal. So this is the direction of ds. This is surface element and its direction is normal drawn to the surface. And electric field is passing through this surface. Now if you see the theta is 0. I mean both E and direction of surface is parallel. Or you can say this electric field is perpendicular to the surface. I'll repeat that. This electric field line E is perpendicular to the surface. See, exactly perpendicular to the surface. Or you can say this is parallel to the direction of surface. Parallel to the direction of surface. See, this is the direction of surface, right? Then, so if this is spherical surface, that we need to notice 2 points. Just see that what the 2 points are. If you choose that surface anywhere, I mean elemental surface anywhere, not only here, but anywhere also. So that E will be normal to the surface. Here also, that electric field line, if you draw the electric field line E, here also that will be normal, like here. Here that electric field is perpendicular to the surface. Not only there, at anywhere on the surface, always this E will be perpendicular. What does it mean? Anywhere this theta will be equal to what? 0. Whether it is here or whether you are choosing somewhere here, here also the theta will be equal to what? 0. And not only that, if that, I mean, if you explain that mathematically, so that E dot ds is equal to what? E ds cos theta. Here the theta is 0, so E ds. And the second point that we need to notice is E will be constant at any point on the surface because the distance will be same anywhere because it is a spherical surface. R will be same. If R is same, why that E will be constant? Just see the equation. Electric field E is equal to what? 1 by 4 pi epsilon naught. Of course, all they are constant. Q by R square. If this distance is everywhere same, Q also constant, this is also constant, and R is also constant. So E will be also constant. What does it mean? At any point on the surface, E remains same, E is constant. Now we are going to apply this. We are going to apply these 2 points in this to calculate the electric field. See here, actual Gauss law is equal to what? That flux through that closed surface is equal to closed surface integral E dot ds. As per this second point, as per this second point, as per this second point, you can write this E out of the integral because E is constant and remaining what? Integral ds. You can write the electric field intensity out of the integral and the remaining will be integral ds. If the surface is spherical, if the surface is spherical, surface area of sphere is what? 4 pi r square. Right? We'll write this. If you write this, E will be what? E will be 1 by 4 pi epsilon naught q by r square. I mean, just here, I will try to figure out that in detail. I'll start from here. So E is constant, so I'll write that out of the integral. Closed surface integral ds is 1 by epsilon naught times q. So this E will be equal to, I mean, E is the total surface area is what? 4 pi r square. 4 pi r square is equal to 1 by epsilon naught times q. Now take this 4 pi r square at right side. So equation will be here. 1 by 4 pi epsilon naught q by r square. So this is calculation of electric field by applying Gauss law of electrostatics for point charge. Now we will try to do that for one-dimensional charge distribution, line charge, right? So if this is line, if total charge is Q, then the charge density will be rho L, total charge per unit length. Now because this is one-dimensional wire, so we should not take volume, we should take only L. So then this Q will be equal to what? Rho into L. If this is only small, if you select small segment of dl, if small segment of dl, then charge will also be dq, right? This is clear. Now we take that line. I mean, this is the line we are considering, that infinite line. I mean, there should be some infinite line. So for this infinite line, the better Gaussian surface is cylindrical surface. The better Gaussian surface is what? Cylindrical surface, right? So the electric field will be what? Away from the cylindrical surface. If you choose here, this is E, away from the away from the cylindrical surface, direction of electric field. You see another part of the surface, this is the direction, away from the cylindrical surface. This is the direction of electric field, right? This is the direction of electric field, or you can say direction of D. And now you can divide this total cylindrical surface into three segments. See here, this is circular surface 1, right side, circular surface 2, left side, and that cylindrical surface around the line is 3. Now we need to apply that Gauss law for the three surfaces because Gauss law is for surface, but here there are three surfaces are there. So we need to apply the Gauss law for three surfaces, right? Uh, if you apply that, so the total charge will be equal to what? As per Gauss law, Q is equal to, now you are going in terms of D, this Q is equal to surface integral D dot ds, and you can write this Q as from here, this Q as from here, rho L dl, rho L dl. So here the total length dl will be equal to what? L. And the left side of this equation is d ds. And here see that interesting. This rho L dl is equal to the surface area of cylinder is equal to what? 2 pi RL. 2 pi RL. So that d is equal to rho L by 2 pi R. This is in terms of d. In terms of d. Even you can write that in terms of electric field also with this relation. D is equal to epsilon naught E. So that E will be equal to what? Rho L by 2 epsilon naught R. But we calculated the electric field intensity only due to cylindrical surface. What about this circular? What about the circular, through the circular surface, what is the flux? We didn't calculate it. We ignored that because if you see, if you see the circular surface, 1, this is the direction of electric field. And this is the direction of surface ds. Right now here, the angle is what? Angle is 90 degree. If theta is 90 degree, cos 90 equal to what? 0. So there will be no flux through the circular surface. Not only this, here also. This is the direction of electric field and this is the direction of surface. Both are separated by 90 degree. Cos 90 is 0. So flux is 0. Flux is 0 in the sense there are no field lines passing through this surface perpendicularly or parallel to the direction of surface. So that's why we didn't calculate the flux for both the circular surfaces, right? And the this is two-dimensional charge distribution, infinite sheet like this. The dotted lines are infinite sheet. And for that, if this is, that what does it mean? The charge is distributed. I'll just redraw it. The charge is distributed on the surface. So if the charge is distributed on the surface, definitely that electric field will be either upward direction or somewhere I will draw here or downward direction. So this is the direction of electric field, or you can say D. So in order to calculate the electric field intensity due to this infinite sheet of charge, now you are considering a small segment, small volume. So I'll write that a little bit bigger here, a little bit bigger here. You're considering a small volume. Now see here, there are six. Now for this Gaussian surface, there are six surfaces are there. The first one is top surface, bottom surface, two. Third and fourth are two side surfaces. Fifth and sixth are front and rear faces. Front and rear faces. Right? But however, that electric field direction is either upwards or downwards. So electric field intensity either upwards or downwards. Now we'll take both top and bottom surface. See here. This is the direction of top surface and this is the direction of bottom surface. Now they are exactly perpendicular. They are exact. These directions are exactly parallel to electric field intensity. That electric field intensity is, or you can say electric field intensity is perpendicular to the surface or parallel to the direction of surface. Right? But if you see the two side faces, if you see the two side faces, right? This is the direction of electric field, but the direction of surface is here, ds. Now both are 90 degree, cos 90 is 0. So there will be no flux through the two side faces. And even if you draw the front and rear faces, like this is along the z axis. I mean, electric field is along y axis, but the direction of surface is along z axis. So y and z are separated by 90 degrees. So the conclusion is only only the electric field lines, I'll write here, only the electric field lines is perpendicularly passing through only top and bottom surfaces. So we need to ignore the other four surfaces in calculation. So this is Gauss law in terms of D. Right? Here we should write six integrals because there are six surfaces, but we are not considering all the six surfaces. We are considering only top and bottom only because rest of the surfaces are not, the electric field is not perfectly perpendicular to the rest of the surfaces, rest of the four. So we'll consider only top surface and bottom surface. So let be the surface area of the top and bottom is A and A, some area, L into it, A and A. At right side, this will be also A. So if you simplify that, D is equal to rho S by 2. Or in terms of electric field, you can write rho S by 2 epsilon naught. So by applying Gauss law of electrostatics, you can calculate or measure the electric field intensity due to charge distributions. That is the advantage. Charge distribution. The charge distribution may be one-dimensional or two-dimensional or whatever. So this is the overall electrostatics. We see the Coulomb's law, relation between electric field intensity and electric potential, then Gauss law and its applications. Thank you.